problem we are solving today is basically a torsional system made up of composite shafts. Um, let's look at the system. This is a steel shaft, the first part, and this is 60 centimeters long. Inside this steel shaft is an aluminium core, okay, and this steel shaft outside is about 40 millimeters, inside is 20 millimeters, okay. So after this, this steel shaft is attached to 80 centimeters another steel shaft which is solid steel. So let's look at this. This is another steel shaft. This is about 80 centimeters. This steel shaft is attached to a blob of mass. Let's call this blob mass M. Okay. And at the very end, this mass is attached to another shaft of aluminium which is about 120 centimeters long. So this is 120 centimeters long. Okay. And let's name this as points A, B, C, D, and E. So again, this is made up of steel. This is also made up of steel. This is made up of aluminium, and the inside core of this is also aluminium. Okay. So what we want to do in this is we want to model this system. Okay. Model this system in vibrational terms. So how do you model this? By model, what I mean is to develop a mathematical model, you will need to find the torque in every part of this system, as well as overall what is the overall torque and what is the deflection or angular deflection, which is theta. Okay, so the best way to find both this is to find the torsional stiffness. So K is the equivalent torsional stiffness of this entire system, which is equals to the torque over the angular deflection. Okay, so this is what we want to find the equivalent torsional stiffness of the entire system. What we will do is we'll proceed with finding the torsional stiffness of each of these sections. So section AB, section BC, and section DE. Okay, so we'll find the torsional stiffness of each of these, and then we'll combine together to find the equivalent stiffness of the entire system. So let's start with the section AB. For the section AB, what is given is the radius RAB, which is the inside aluminium core, which is about 20 millimeters. Then the radius outside is given as 40 millimeters. Okay. Then the material properties, that is G of steel, is given as 80 gigapascal GPa, or 80 into 10 to the power 9 Newton per meter square. Similarly for BC shaft, BC, it's a solid steel shaft. The radius RBC is given as about 18 millimeters. Okay. For the section DE, which is aluminium, the G of that is given as 40 gigapascal, so 40 into 10 to the power 9 Newton per meter square. Okay, so we want to proceed to find the stiffness of each of these sections. So let's look at the AB steel part. Okay, is how you can find this. So the way to find this is very simple. We'll use the basic equation, that is torque over theta is equals to JG over L. J is the polar moment of inertia, G is the modulus, L is the length of the shaft, T is the torque, and theta is the angular deflection. So this you can find that way you can find the stiffness. So KAB of steel is then equals to JAB times G of steel divided by the LAB. Okay, so JAB is the polar moment of inertia, so that is equals to pi over 2 the outside radius, which is about 40 millimeters, 0.04 to the power 4 minus 0.02 to the power 4. Okay, and you know what is the steel modulus, which is given to you already, 80 gigapascal. The length of this is about 60 centimeters, so length can be about 0.6 meters. So KAB of steel comes out to be 5.03 into 10 to the power 5 Newton meters per radians. Okay. So this is for the steel portion. Similarly, you can find for the aluminium portion, which is the inside core. So for the aluminium, again same equations are used. So JAB of just the aluminium, then G, the modulus of the aluminium portion, and the length of this will be the same. So KAB of aluminium comes out to be equals to 1.68 into 10 to the power 4 Newton meters per radians. Similarly, for the portions KBC and KDE, you can find the modulus. Okay, in same fashion, KBC and KDE. Okay, now once this part is done, what you want to do is you want to move on to find the stiffness of the entire section. So how do you do that? Well, what you do is, first of all, consider the portion AB. So if you look at the portion AB, let's look at the figure again. This is made up of steel on the outside, and inside is the aluminium core. So basically they are connected to each other, and so they will have the same angle of deflection or angle of twist. Okay, so that means the stiffness of each of these will be added together. Okay, so the stiffness of the entire AB portion, KAB, will be equals to stiffness of the steel portion plus stiffness of the aluminium portion. Okay, now for the portion BC, ABC rather, these shafts are basically connected to each other in such a way that the angle of twist or the deflection angle is going to be different for each of these two shafts. So if you look at, say, AB, which is made up of composite beam steel and aluminium, and then this is a solid steel portion BC, they will have different angle of twist. So that means they are in series. Okay, so the stiffness of each of these can be found using the normal equation, which is 1 over K ABC will be equals to 1 over KAB plus 1 over KBC. Okay. Now CD is the collar or the blob of mass which is connected to this portion. So let's look at this again. This portion. This is the blob of mass. Okay. The way it is connected is the angle of twist for the entire portion before C and the angle of twist for the entire portion after D is going to be the same. So that means that these two portions will be in parallel. So the equation then for the equivalent stiffness of the entire system will be equals to K equivalent is equals to KABC, which is the portion before the blob of mass, plus KDE, okay, because these two are in parallel. This is the final equation, and that's how you can find the equivalent stiffness. Thank you.